So this is Math 110, Section 2.3, day number 2. And we are going to be talking about the worksheet that you should have either looked at on Angel, have it on your computer screen, or print it out, because it's not all that clear up here. It'd be better if you have a hard copy in front of you. And we started 2.3 on Wednesday, so this is just the continuation of it. The first question on this sheet is a review question. So just to make sure we're all clear about what we did on Wednesday. If you have a function and are asked for the average rate of change, this is an algebra question, average rate of change. All you have to do is remember that average rate of change is f of b minus f of a all over b minus a. That's the definition of average rate of change. It's a slope. So what you would want to do is take your b value, which is 8, and plug it into your function. So it'd be 3 times 8 squared minus 4 times 8 plus 6. That's f of b. Then you're going to plug a into your function, which is 6. And so you're going to get 3 times 6 squared minus 4 times 6 plus 6. And you're putting that all over b minus a, which is 8 minus 6. You have to calculate that out and come up with a value for that. So I'm going to grab my calculator and figure out what that is. So I have 3 times 64 minus 32 plus 6, so that's 166. And then I have 3 times 36 minus 24 plus 6, which is 90, all over 2. And 166 minus 90 divided by 2 looks like 38. So the average rate of change in this function is 38. That's the f of b minus f of a over b minus a, or you can also think about it as the slope of the secant line, like we talked about Wednesday. The instantaneous rate of change. When you see this, this is calculus. This is the slope of the tangent line. So this has to do with the derivative. So we have to take our function and figure out its derivative first. And we're going to use the power rule. We're going to pull the 2 down. 3 times 2 is 6. Drop the degree from squared to the first power. We're going to pull the 1 down. Negative 4 times 1 is negative 4. Drop the degree to 0, which means there is no x. And the derivative of 6 is 0, so I'm not going to write that. So once I have the derivative, all I've got to do is evaluate it at the number 7 to get the slope of the tangent line when x is 7. 6 times 7 minus 4. So I end up with 42 minus 4, which is also 38. And so it turns out in this case, the average rate of change and the instantaneous rate of change was the same, but that is usually not the case. So that's a quick review of what we did on Wednesday and what you needed to know. What we're moving on to today, the second day of this section, is the economic implication of what we've been talking about. So there are rates of change in economics that you need to know that are called marginals. So P, capital P, we know is our profit. That's what we use for profit. So if we say dP dx, the derivative of profit with respect to the number of units made is called marginal profit. And the idea of marginal profit is the profit made from selling one more unit. So in other words, if I am evaluating dPdx when x is 100, marginal profit would be the profit I'm going to make from selling 101 units, that next unit. One more unit than I've been selling. Marginal revenue, same idea. The change in revenue with respect to the number of units that I am selling. So the revenue I'm going to make from selling one more unit. And if I know what x is, if x is 75, it's the revenue I'm making on the 76th unit, that next unit. And the same thing for cost. The marginal cost is the cost of making one more unit. How much is it going to cost me to make this next unit? Well, hopefully you remember that marginal cost has another name. It's called fixed cost, because I know what it costs me to make every unit that I make. So in the problems that we've done, that's not an unknown. I know what my fixed cost is. I know what it costs me to make the next unit. Marginal revenue, I know what that is too. The revenue I'm going to make from selling another unit, that's price. Okay, whatever the price is, that's what I'm getting in every time. So those two things are not something we haven't thought about before, but just so that you need to know this idea of marginal, and it has to do with derivative. So for example, if somebody hands me a profit function, they said that if you tell me how many units that you sell, if you plug it in here, it'll tell you what your profit is. So if I want marginal profit, the profit from selling the next unit, I want to take the derivative. I want to take the derivative of this profit function with respect to x. So I'm going to use the power rule again. I'm going to pull the 3 down, 0.0006, and I'm going to drop the degree to x squared. Plus, I'm going to take the derivative of 10x, which is 10. So this is my marginal profit function. And now I'm going to evaluate that marginal profit function at the number 50. That'll tell me the marginal profit when x is 50, or the extra profit I'll make by making the 51st unit and selling it. So that's 0.0006 times 50 squared plus 10. And so when I calculate that out, I get $11.50. So if I make the 51st unit and sell it, my marginal profit says I'll make $11.50 more. Comparing it to the actual gain. The actual gain in profit is what I would make if I sold 51 units minus what I made when I sold 50 units. This is the actual change in profit. It's not a calculus problem, it's just a straightforward problem. What did I make? What profit did I make for 51 units? What profit did I make for 50? And I'm going to subtract them. So in this case, I'm plugging back into my original profit function. I'm going to get the profit for 51 units is 0.0002, 51 cubed plus 10 times 51. And the profit for 50 units was 0.0002, 50 cubed plus 10 times 50. So I'm going to calculate both of these values and then subtract, and I'll figure out my actual gain. The marginal is what I'm expecting to happen when I go beyond the 50 units that I've sold. The actual gain is what actually happened with my profit function. So I've got 0.002 times 50 times 50 times 50 plus 10 times 50. This bottom one is 525. And then 0.0002 times 51 times 51 times 51 plus 10 times 51. This was 536.53. I'm rounding it off because there were a couple digits after that I'm going to drop off because this is money. I don't want to have too many digits. I'm going to subtract those two answers and I get $11.53. It's close to my marginal profit, but not exactly the same, because this is a difference in Y values on the curve. This has to do with the derivative, the slope of the tangent, which is not on the curve. So these two values came from the curve, the profit function curve. This value came from the slope of the tangent line, which is not on the curve. And that's the difference between the two. So, for example, if you have a function that goes like this, and I ask for the marginal, what you're doing is you're approximating the curve with this tangent line. And so if this is, say, 50 units, and you want to guess what's happening, what profit is at the 51st unit, you're here on the line, on the tangent line if you're using derivative, as opposed to being on the curve itself and finding the difference in those two Y values. So you're going to have a bit of a difference when you use the derivative because you're not on the curve anymore, you're approximating things with a tangent line. And you know to do that when you see the word marginal. Okay, the demand function. A demand function we've talked about before. It's the number of units that consumers are willing to purchase at a given price. So it's a function of X. And the revenue function that we've talked about before takes that demand function and multiplies by X. So it's been the case, at least in the first test, where I let little p be a price, a constant price. But there's sometimes when the demand function, the price and the number of units sold, are related to each other in a way that we come up with a function for p instead of a number for p. And so if we're trying to come up with a revenue function, that demand function becomes a part of it. So we take the demand function times the number of units to get revenue. So here's an example of a situation where we might have to do that in order to come up with a demand function and a revenue function. So the problem says that a business sells 2,000 items per month when the price is $10. It's estimated that monthly sales will increase 250 units for every 25-cent reduction in price. Use this information to find a demand function and a revenue function. Well, in terms of this problem, these two words are key. The words for each. When you see for each, it means that you have a linear function. Because it's saying that every time you drop the price 25 cents, you sell 250 more units. Well, that's not reality. In reality, things don't happen in a linear way like that. If you drop the price from $20 to $11, to $19.75, maybe you'd sell 250 more units. But if you dropped it again, 25 more cents, probably not going to make exactly 250 more units. So this again is one of those simplifications of reality that helps us be able to do the problem with the little bit of math that we know. So we're going to be simplifying things and making this demand function a line instead of a curve like it should be. So how do we come up with the equation of the line? Well, we've got 2 points, and anytime we have 2 points, we get an equation of a line. So here's 1 point. 2,000 items with a price of $10. We have to remember that we put our units on the x-axis and our money on the y-axis, just like we talked about at the beginning, which means our x is going to be x on the x-axis, but our y is going to be the p, or the price. So we want to think about y, if we're going to write the equation of a line, we're going to call it p instead of y. It's the price. So our points are 2,000, which is x, matching with $10, which is my y value. And then if I'm going to increase sales, $250, or 250 units, that means I'm going to now sell 2,250, but only if I drop the price to $9.75. So here are 2 points that I have from the words that I had up at the beginning. 2,000 units when the price is 10, 2,250 units if the price is $9.75. And if I have 2 points, I can come up with a slope. And if I have a slope and a point, I can come up with an equation of the line. And that's where I'm headed next. My slope is the one y value minus the other y value over the matching x value minus the other x value. So you want to match the 10 with the 2,000 and the 975 with the 2,250. You're going to subtract and divide and get a slope. So my slope is going to be negative, because when I subtract 10 minus 975, that's positive. But when I subtract 2,000 minus 2,250, that's negative. And I'm going to end up with 0.25 over negative 250, which is negative 0.001. Or if you like it better, negative 1 over 1,000. So that's my slope. My equation of my line now is, instead of y, I'm going to say p minus the p-value of the first point equals the slope times x minus the x value of that first point. And that is my demand function. I can rewrite it if I need to, and I think I will have to rewrite it because I am trying to come up with a revenue function next. So I'll make it say p equals. I'll distribute, oh, I forgot my negative, I'm sorry. That's a negative slope here. I'll distribute my slope through negative 0.001x. I'll distribute this through, not forgetting my negative. So I have 2,000 times 0.001, which is 2, and it's positive, negative times negative. But I also have to move this 10 over. So I'm going to add 10 to both sides as well, so that it says p equals instead of p minus 10. So when all's said and done, there is my demand function. It's relating the price and the number of units sold. If you tell me how many units I sold, I can tell you what the price was, which isn't always as helpful as knowing, if you tell me the price, I can tell you how many I sell. That's a little more important, but for now, here's the demand function in terms of P. My revenue function is P times X. So price is not a static thing. It's not like I'm selling these things for $10 no matter what. Price is a function of X. in this case. So my revenue, I have to take that function of X and multiply it by the number of units I sold. And this is how I'm going to get revenue as a function of X. I'm going to get negative 0.001 X squared plus 12X if I decide to distribute through. Whether or not you distribute through is up to you. So this is a skill that you have to have. You have to be able to take data that I give you, write a demand function, take that demand function and turn it into a revenue function. And the process is always the same. So you need to practice it until you're able to do it. We're going to be doing it with different types of functions, but in this, for now, it's just a linear function. If you have a linear demand function, you need to be able to find it and then turn it into a revenue function. So again, the steps are, use the data that I gave you to find 2 points that you know are on this demand function. Use those 2 points to come up with the equation of the line. And once you have the equation of the line, then you multiply it by X to get your revenue function. If there are any questions on that, we can go over that Monday. But that should help you with your homework. The next example. Maybe I'll just give you a demand function. I'll just hand it to you. You don't have to find it yourself. If I just give you a demand function and then I ask for marginal revenue, then what you've got to think is, well, I can't get marginal revenue unless I first have revenue, because marginal revenue is the derivative of revenue. So I got to get revenue first. And I can't get revenue unless I know demand. But I do know demand. Somebody gave it to me. So the process is, if I want marginal revenue, I've got to figure out revenue. If I want revenue, I have to take X times P. So then I look up at the problem again. Oh, they told me what P was. Good. I have to take this times X, and that'll be revenue. And once I've done that, I need to take its derivative, and that'll be marginal revenue. So my revenue function is my demand times X. And I need to simplify that a little bit because I have to take its derivative. And right now, I can't take the derivative when it's written as a product. I have to simplify it. I only know the power rule. So I'm going to have to distribute my X through and simplify. The other thing is, it's helpful, like I talked about previously, to know what the coefficient is, or that number that just sits out in front. And if you have 2,000 in the denominator, it's the same thing as 1 over 2,000 times what comes next. So I can think of this fraction like this. I can pull that fraction, the constant part of it out, and make it 1 over 2,000. And then what's left, my 60,000 minus X, can get multiplied by X. So I'm pulling it apart so that I can see it in a way that it's easy to take the derivative of. So I have to distribute in order to take the derivative, unless I know more calculus than has been taught in my class, because when you try to take the derivative of a product, that's a tricky thing. And so rather than doing that, I'll just multiply that X through, and now I can just use the power rule here and the power rule here to find the derivative. This is my constant multiple, so it's just going to come along for the ride in my answer. So my derivative is, I'll call it R prime, or if you prefer, you can call it dr dx, the derivative of revenue with respect to this variable, X. And I end up with 1 over 2,000, because that's a constant multiple, it just stays there. Take the derivative of 60,000x, which is 60,000. Take the derivative of x squared, which is 2x. And to finalize my answer, they wanted marginal revenue, which I have, but when 2,000 units are sold, I'm sorry, 20,000 units are sold. So when X equals 20,000, because X is always the number of units, so all I got to do is plug 20,000 in for X. So my final answer is 1 over 20, or 2,000 times 60,000 minus 2 times 20,000. Plugging that 20,000 in for X. So I'm going to get 1 over 2,000 times 60,000 minus 40,000, which is 1 over 2,000 times 20,000, which is $10. So in other words, if I sell the 20,001st unit, that next unit, I should make $10 in revenue. That's not profit, because I don't know what it's going to cost me to make that next unit, but that's how much money I should be bringing in revenue. So the process again is, if you need marginal revenue, you need revenue first. There's no way to get the marginal revenue function without the revenue function. If you need the revenue function, you need the demand function, because revenue is demand times X. So I took the demand function they gave me, multiplied it by X to turn it into revenue, took its derivative, and plugged in the value they wanted me to plug in. And that's the steps to go from a demand function to a marginal revenue value. And then the last example, which should help you again on your homework, is example number 4. If you're given a cost function, so in this case, my fixed cost is $5,000, my variable cost is 56 cents. So this is assuming that it's going to cost me 56 cents to make every unit that I make. And I'm given the demand function from example 3. I want the profit function. And then I want marginal profit. So again, we've got to think through, how do I get a profit function? Well, a profit function comes from a revenue function minus a cost function. So if I know the revenue function for example 3, which I do because it's right here, or even better right here, simplified version of it here, and I know the cost function, which they gave me, then I can come up with profit. So this would be fairly simple. I'm going to take my revenue function from example 3, which was 1 over 2,000 times 60,000 x minus x squared, before I took the derivative. It's my revenue function. And I'm going to subtract my cost. Now, the biggest problem with subtracting cost from revenue is people who forget to distribute the negative. So we're going to make sure we distribute a negative to the 5,000 and a negative to the 0.56x. So we are finding profit by taking the revenue function from 3 minus the cost. And then they asked me for the marginal profit function. So I need the derivative of this. But since this is subtraction, I can take the derivative of this piece minus the derivative of this, which is 0, minus the derivative of that. So taking the derivative won't be any harder than it was up in example number 3, because I'm going to think about the 1 over 2,000 as a constant multiple of this first part. I'm going to take the derivative of 60,000x, just like I did up top, and the derivative of x squared. Minus the derivative of 5,000 is 0. The derivative of this is 0.56. There is my marginal profit function. And I can then calculate that marginal profit for any particular value of x that they want. And so if you're given a cost function and you know a revenue function, you can always come up with profit, just like you did on Chapter 1 test. The only difference is our functions are going to start to get a little more complicated than they were in Chapter 1. So that is the end of the material that I was planning on presenting in class on Friday. And it should be enough to get you through the homework assignment, the web assignment, which is due Monday. But you can bring any questions that you have on either of the 2.3 assignments, day 1 or day 2, on Monday. We'll go over those questions before we move on to the next section.